Welcome to the Passive House Podcast, brought to you by Passive House Accelerator, a catalyst for zero carbon building. For news, inspiration, and connections from all flavours of Passive House, check out passivehouseaccelerator.com. Sign up to receive regular updates about events, get your questions answered, and contribute to the community dialogue. There's loads of free information for experienced professionals and people just starting out on their Passive House journey. We hope to see you at one of our weekly Passive House Accelerator live webinars. In the meantime, here's this week's Passive House Podcast. Welcome back to the Passive House Podcast. I'm Matthew Cutler-Welsh, coming to you from Auckland in New Zealand, and I'm joined this week by Zach Semke. How you going, Zach?
I'm doing well. Hello.
And also Mary James. How you go, Mary?
Oh, I'm good. I'm not in Southern California. I'm in Northern California, so avoiding those.
Yeah. It sounds pretty full on. I've kind of been off the news because it's sort of summer break here, but it's kind of hard to avoid some social media posts and seeing some images of some pretty scary images of fire very close to houses this time. It's not one of those fires that's sort of away in a forest somewhere. It seems like there's a lot of people being pretty severely affected this time around.
Yes, it's very scary.
Yes, and of course we've talked quite a lot about this in the past about the need, and I've actually been catching up on some other podcasts over my summer break here, some other building science podcasts and energy efficiency podcasts, and the issue of indoor air quality does come up quite a lot, and the importance of ventilation and air infiltration. I know that, Zach, we've talked about that. Kind of keeps coming around again and again about that need to get some filters and have something in place to keep those toxic out of the house.
Yeah, no kidding. I mean, you think about how toxic just wildfire smoke is from trees burning, but now you have like entire, all of the materials in an entire community going up in flames. I mean, it's there's a image that I saw of a McDonald's with the Santa Ana winds just blowing these inflamed palm trees, and then the sign, one of the McDonald's signs burning, all that plastic, and it's just like it's really super nasty and yeah, pretty apocalyptic scenes going on. So yeah, we talk about fire resilience. I mean, I don't think there's the resilience to the smoke, obviously, and obviously we need to fire harden. But in these circumstances, I don't see how any fire hardening would save some of the structures that were in Pacific Palisades. I mean, it's an entire community that's just wiped off the map, basically. Yeah. So yeah, pretty sobering.
Very sobering. Well, we've got something, of course, it's all related in some ways, but changing tack a little bit to today's conversation. We're going back over to the UK, and I really enjoyed this chat. I found it a little bit more motivating and inspiring. So we'll get into that in a moment. But before we do, we've got a few people to thank, Zach.
Indeed. So I want to thank Be Public Prefab. Be Public is our accelerator partner of the week. So thank you to Be Public for their support of our programming this week. And Bewizo is the sponsor of the week. So also a big thank you to Bewizo for making everything happen for us at the accelerator this week, including this episode of the Passive House podcast. And I'd like to take a moment to thank our sponsors, the fine organizations that make our work possible. So a thank you to our stakeholder partner, NYSERDA, the New York State Energy Research and Development Authority. Thank you to our founding sponsors, 475 High Performance Building Supply, Ingwe Architecture, Partel, Rockwell North America, and Zola Windows. And thank you to our champion sponsors, Bewizo, Icon Windows and Doors, Intelligent Membranes, and Source 2050.
All right. Mary, how did you meet Chris Swinburn?
I met him at the UK Passive House Trust Conference last September and heard him talk. So yeah, that's how I got this interview going.
And just a couple of notes before we dive in. We talk about some temperatures here, so I just need to convert those for
Thank you.
American context. So it was an interesting point that Chris made, and we'll get onto this towards the interview, just about the the less extreme nature of the climate in the UK at the moment. He talked about 30 degrees being pretty warm, and they did reach temperatures of 40 degrees. I know what that means, having grown up in Australia. 40 degrees is very, very uncomfortable. In a place that is not used to those sorts of temperatures, I can imagine it's even more uncomfortable. So 40 degrees Celsius, that's over 100 degrees Fahrenheit. It's 104 degrees Fahrenheit. Even 30 degrees Celsius is 86 degrees Fahrenheit. So that's getting right up there. And if you had a couple of the days of that temperature in a place that doesn't really have air conditioning, is not really used to keeping cool, then that can have some pretty significant implications on comfort. So hopefully that little translation is helpful. And with that, we'll dive in to Mary, your conversation with Chris Swinburn.
Okay, well, welcome to the Passive House podcast. I'm Mary James, and I'm here with Chris Swinburn, director of Beyond Carbon, which is based in Bicester in the UK. Can you please introduce yourself and tell us what Beyond Carbon does and why you founded it when you did?
Yeah, so we founded Beyond Carbon nearly 3 years ago. My background is in mechanical engineering, and I was a building services engineer for sort of 12 years before moving into being more focused on sustainability and then specifically focused on passive house design. And we founded Beyond Carbon really off the back of coming out of a previous practice and a feeling that we could do passive house consultancy in a more focused and kind of values driven way, and wanted to build something that would be dedicated to making genuinely low energy buildings that have minimal impact. And so here we are 3 years on. There's now 16 of us and a couple more on the way. And we're working on all kinds of passive house projects, and from offices to student residential to labs. So it's been a great 3 years of being able to build and do the sort of thing that we set out to do.
Yes, and as you mentioned, you've done labs and student residences, and essentially your firm only deals with more complex passive house buildings and larger scale ones. What led to that choice?
I think in some ways it was accidental, in the sense of that my fellow director Joel Callow and I both came from practices that were doing only commercial scale buildings. So it was building services led practice, and building services consultancies do almost exclusively larger scale projects. That's the only kind of model that generally works in terms of that sort of consultancy work. So we came from that world, and we were therefore used to engaging with large buildings and the complexities of tier one contractor projects and projects that involved complex building services, facades, structures, and all of that. So we weren't afraid of that world. I think we were quite familiar with it. So it seemed quite a natural fit then to start applying passive house principles to that, in terms of how do we make these buildings low energy and ensure enough to actually achieve passive house certification on those buildings as well. So it was once we got into that, we realized that we could do it. There aren't that many doing buildings of that scale with passive house, certainly not as a dedicated consultancy. So we felt that we were pretty uniquely placed to be able to influence that world, and we weren't sort of worried about the scale of the projects.
And are all your projects exclusively passive house?
Not exclusively, mostly. So I think probably about 80-90% of our projects are passive house, but we do have we have some projects that are passive house but not certified, which is a whole other area of discussion. But for whatever reason, that passive house certification wasn't sought, but they're pursuing a similar process to passive house. And we have some projects that are retrofit that aren't meeting a standard accreditation, but are still deep retrofit. And then we have some more strategic type work which is not specifically passive house, but more general kind of low carbon strategy work.
Well, I definitely want to talk about your deep retrofit work a little bit later in this podcast. But I also wanted to ask, for now, are all your projects 100% electric?
Yes, I mean we I'm trying to think if there are any examples the other way that are hiding in the woodwork, but we actually have a policy. We're signed up to no more gas, whatever the phrase is. That means that we won't work on projects that have new gas boilers, new gas boiler installations going into buildings, new or existing. Now, there's always going to be there's times when they might have to make exceptions, but so far we haven't. I don't think we've broken that rule. Every project we work on has heat pumps or some form of electric heating for hot water and space heating.
That's great. And I looked this up just because I was curious. The UK energy mix is creeping up on being 50% from renewables. It's not quite there yet. According to the data I saw, 43%. So it's not only electric, but, a large majority of your energy mix is coming from wind, biomass, solar.
Yeah, and this is a kind of crucial point, really, is that we are working on this assumption that is so far proved reasonable, that our electricity grid, certainly in our country, is decarbonizing, and it has done dramatically so in the last 10 years. It may be slightly stalled at the moment. We've seen not that much change in the grid carbon factors in the last year or two, but that's still the hope, that there's still lots more investment to come in offshore wind and other forms of low carbon energy. So that's kind of the basis of which we therefore believe, and as I say, this is industry-led practice, that heat pumps connected to a decarbonising grid are the way forward. We simply can't rely on fossil fuels being burned to generate heat anymore. That option is not one we can take. And other pathways, for example, hydrogen, don't seem to have much merit at the moment. So heat pumps on a low carbon grid is kind of seen as the way forward. But you're quite right; it does depend on that grid continuing to decarbonise, which is a matter of government policy and other things as well.
Of course. And so when I was at the UK Passive House Trust conference, I heard you give a talk on a residential complex that you guys worked on at the University of West England in Bristol, which anyway, at the time of the talk was one of the largest or the largest passive house building in the UK. And can you tell us a little bit about that project?
Yeah, of course. It is, I think, officially or unofficially, the largest passive house development in the UK, when you add all three buildings together, at least. And I'm told that even one of the buildings actually is on its own is the largest in the UK. But that might just be hearsay. But we're clinging to that title for now. It's a student accommodation project in Bristol for UWE on their Frenchay campus. 900 student accommodation bedrooms, about 26,000 meters squared, GIA. I can't convert that into square footage, I'm afraid, for US listeners. But it's a pretty big development in student accommodation terms, and in passive house terms, it's huge. And it started in 2019, so it's been a long time sort of coming. It's now finished and occupied, and more or less fully occupied as well. It takes a bit of time to fill student accommodation, tends to be phased and sort of gradually fill up, but it is, I'm told it's sort of 95% fully occupied all the time. And yeah, it was sort of my first project of scale, I would say, in terms of passive house. So really it was all about how do we take the principles of passive house you might apply to residential buildings and scale them up for large buildings that have particular techniques of construction that are not maybe naturally wedded to low energy design. And how did we deliver a building which is really low energy and works? How do we pass those air tests on something so huge?
And just for our audience, it's really a complex of 3 buildings, correct?
Yeah, sorry. So it is 3 buildings. So the 2 are very similar size. They're kind of a U-shaped building, each something like 8,000 meters squared, and then there's a smaller sort of R-shaped building. So the 3 have got some similar. They're all kind of student accommodation, very similar bedroom types, but the 2 larger blocks have got some extra facilities in them, including some communal areas and a commercial cafe. So there's 3 blocks. They were built, but they were effectively built all at the same time. there was some phasing between them when they were finished, but it was all going up at the same time.
And one of the points of discussion during your talk was just that the scale of those buildings allowed for some wiggle room when you were trying to meet the Passive House criteria. Can you just elaborate on give us an example of what some of those challenges were and how they were addressed?
Yeah, I mean, the main thing is about when you scale buildings up, this magical thing happens with the geometry. I mean, it's literally a mathematical thing that their surface area compared to their usable floor area reduces. So in other words, they get more form efficient, or we say the heat loss form factor, which is the technical term, gets lower, it gets better. So you've got less surface area compared to the area of the floor that you're trying to heat, and therefore you lose intrinsically less heat. And that means that you need less insulation. It means that in effect, it's easier to hit the Passive House standards. Now, I use that term very carefully because it isn't an easy thing to do for lots of reasons. But in terms of the kind of physics of it, you've got something that's much easier to heat. So the insulation levels were, they were pretty normal for the type of building regulations, levels of insulation. The glazing was triple glazing, but it didn't have to be sort of extreme in its performance. It gives a lot of wriggle room, particularly around the facade design. Student accommodation lends itself to having very consistent facades. You can imagine you can't really have student bedrooms that are hugely glazed and others that have barely any glazing, whereas traditional Passive House design for small dwellings would want you to do exactly that, to increase your glazing on the south facade, reduce it on the north. That doesn't work if you're trying to provide a sort of equal experience for students and the visual that works. But the fact that we had this really good form factor meant that just everything about the building was less sensitive for space heating, so we could play a lot more with the glazing, focus more on getting good daylight, controlling overheating and that sort of thing. So it kind of brought us a lot more. I mean, wriggle room is the perfect phrase. It just gave us a lot more room to maneuver on the specification and design of the facade, allow us to focus on other things that were important. We did do some things as well that made our life a lot easier. So the facade is very lightweight, which means we don't have big brackets and all of their thermal bridges that go with them. And there were some very intentional points that we knew would make our life easy from the beginning, rather than kind of tying us into things that would put pressure on the specification.
And can you talk a little bit about the mechanical system choices that makes this building work? Especially, I mean, we had a little discussion about the water heating because you talked about, yes, you're going to be using a lot of heat pumps, mostly heat pumps in your buildings, but this one, you did use heat pumps for heating. You don't have active cooling, is that correct?
Yeah, that's right. So we have the heat pumps actually do just the hot water. So the heating is in fact direct electric. So there are panel radiators in each student bedroom. They've got a clever controller that goes with them, so to minimize their use, so it can detect whether there's someone in the room, and then it can drop the set point if they're not there. It detects if there's a window open, it detects the airflow into the room, and it turns it off. It does things like that. So we have these smart controls with a local radiator, electric radiator. The reason we did that was effectively cost. It was a value engineering process to get the most out of this design. And we collectively looked at this and thought, well, actually, we've done all the hard work with the fabric for Passive House of getting the energy demand for heating that so low that if we now supply it with a direct electric heater instead of a heat pump, even though it's going to, in theory, use 3 times the energy of a heat pump, we're talking 3 times a very small amount. And the cost reduction that was achieved from that was very significant, as well as the ongoing maintenance reductions from not having to manage a whole radiator system, which the university had some quite bad experience of. So they really liked that. It saved money. And these controllers, they've also had a lot of success with giving the students good control, but also being able to keep an eye on energy costs. The hot water, however, was a heat pump system. So that we recognize actually the hot water energy demand in the building is more than the space heating in a student resi Passive House. So actually we're focusing on the thing which uses more energy in the first place, just the sheer demand for showering, the thing you can't there's limited control over. We put in low flow showers, but in the end, there will be showers. This is the amount of energy that's going to be used. So how do we deal with that? So we have carbon dioxide based heat pumps. Carbon dioxide is the refrigerant, so it's got a global warming potential, obviously, maybe not obviously, but of 1 compared to CO2, because it is CO2. So, a really environmentally sustainable form of heating hot water. For that reason, we're not so worried about refrigerant leakage and so on. And it makes it more efficient for the hot water temperatures that we're trying to achieve. So all the hot water is generated by these CO2 heat pumps, and then is pumped around the building. I'll come on to that. That's definitely an area that we felt there's more work to be done in the industry on that sort of system to improve its efficiency. But it's certainly very low energy, low carbon compared to traditional gas boiler systems.
Oh, that's great. I didn't realize that you were using that. And I guess in the climate there's no issue with having that carbon dioxide based heat pump, water heater.
No, they're specifically designed for the high temperatures of hot water generation, so they're really efficient. Efficiency
thinking about freezing.
I'll think about Yeah, no. This is the UK. We don't have. It's never very cold. It's never very hot. It's just that sort of mediocre conditions all year round. So we don't have to worry about getting down to -20 or something. That's pretty unheard of here at the moment in current climate.
And you had mentioned briefly a concern about overheating. Was that, here in North America, that's pretty much a bigger concern going forward. Was that something that you worried about much? And if so, how did you address that?
Yeah, we worried about that a lot, maybe for several reasons. One, that student accommodation is renowned for overheating. Secondly, because it's renowned for having hot water pipe work running through it that causes overheating, and we had that precise system going in. And thirdly, because we're anticipating overheating will get worse as the climate changes, or at least it certainly could get worse. So we did a lot of thinking on this area, and how can we not just make the building work now, but also future-proof it. We did a lot of modeling. So I had a colleague who modeled the buildings in huge amounts of detail. We worked really hard together to think about all of the kind of profiles of the usage in those buildings. And the software that you use for overheating modeling it's capable of simulating every 10 minutes of the year if you want it to. So it's pretty detailed, but it's all based on climate data and your assumptions, right? So the old phrase, rubbish in, rubbish out. We work really hard to make sure what we're modeling makes sense. And we tested it against future weather files. So we tested it for 2050 weather files, which incidentally, actually, we don't really think of 2050. We think, given we had a 40-degree summer in the UK in 2022, which is that's unheard of in the UK. Many of your listeners will probably think that's pretty normal, but for us, 40-degree summer, a 30-degree summer is pretty exceptional, and we had a 40-degree summer for the first time, in living memory. So we're modeling this stuff as if it's future, but actually we've just experienced it. We modeled it for 2080 as well, which is a bit of a strange one, because you model for 2080 and you're guaranteed to fail. It's such an extreme condition, but we wanted to see how the building would behave and then how we might future-proof it. So we developed a scheme which is mostly naturally ventilated, actually, for overheating control, sort of a combination of designing the reveals of the windows, the shading on the own windows, to minimize solar gains, give us lots of airflow, and we're able to get that to work really well for 2050. For future conditions, because we've got a centralized air handling system, so MVHR in the kind of passive house parlance, it's possible to add cooling to that system in future. You can bolt on a chiller, you can supply cool air to those rooms, and with that gave us even more wriggle room in terms of future climate change. So a lot of time spent on that. And then the hot water systems, we insulating them extremely well, minimizing the amount of pipe work in corridors and ventilating those corridors as well. It was a pretty detailed exercise. Not guarantee, of course, that the proof will be in the pudding in terms of the actual building operation. We look forward to monitoring that as we go forward. But we felt, compared to what you might normally do, passive house kind of really drives you down this route to think about the occupants and how a building will actually behave.
So you mentioned monitoring. Have you collected any performance data yet? I know it's only just getting fully occupied. So
Yeah. I should say that the project was started when I was at previous practice, and so it was with that practice that I started the project. My former colleagues from that practice, they're doing the monitoring now for the university, but we're in touch with that process and started to see some of the data. So they are monitoring it. They've started to get some temperature data back and some feedback as part of the POE exercise, and the university has also shared with us some of the initial energy data. So all I can say is the energy data so far, we don't have that much of it, but it looks very good in terms of meeting or exceeding the expectations for what we should be using each month. So not much to report on yet, but the initial readings are looking good.
that's great. Congratulations. And now shifting gears a bit, I'd love to hear some more about your refurbishment or retrofit projects, as we'd be more likely to call them here. Could you just, first I'm curious about sort of, are you also working exclusively on large buildings for retrofits? And what's driving the refurbishments or retrofits?
Yeah, so it's more challenging to do large scale retrofit projects because of the way I like to put it is if often clients see it as I've got walls, I've got a roof, I've got a floor, why do I need to change them? There's a functional minimum already provided by an existing building. So the argument then to then upgrade those walls, and in fact more often to take them apart first and then upgrade them, is a challenging one, and that challenge gets bigger on bigger buildings. So we've not seen enough large scale retrofit projects come our way. But on the other hand, we don't tend to do domestic single dwelling retrofit projects. So we have a number of sites and projects where we're looking at some fairly large scale retrofit work. But the one project that's currently on site is a grade 2 listed project for a college in Oxford. And I think in some ways what's driven that to, and I'll explain the depth of retrofit in a moment, but I think what's driven that to go down that route and driven the college to make that strategy is, we effectively as a team, ourselves and the wider design team, I think we've led them to a place where they acknowledge that in some circumstances, and maybe not every building, but where you have an opportunity to innovate in this way, there's a lot of benefits for that, not just in terms of the energy performance you might get out of that building and their bills, but also the kind of multiplier effect and being able to demonstrate what's possible, especially in that case for a building of historic value. So again, accidentally in a way, we've ended up doing retrofit in a very complex building. It's not the largest building actually. It's only a few hundred square meters, so a fraction of the size of the project I just discussed. But it was an example to really push things, and we've actually, in effect, stretched what's possible in the city because it's the first of its kind in Oxford. There are others in Cambridge, for example, have done quite a few. In the city of Cambridge, they've done a number of fairly ambitious retrofits to historic buildings, but this is the first really in Oxford that got permission and sort of to some degree leading the way. So the college is unlikely to do it to every building. In fact, that's not viable to do it to every building, partly out of cost, but other reasons. But that's not the point. It's about, I think, where you have the chance to do exemplar. I mean, this is going to be incredibly low energy as a building once it's complete. Then you can take it and you learn lots from that, and those lessons can be taken elsewhere and have a big influence on others.
And what building use does this building have?
Yeah, so it's a student accommodation, but it's an interesting site. It wasn't always student accommodation. It was originally a house from someone with wealth in Oxford. It was extended several times. In different periods. There is 16th century parts of the building, I think some of the oldest parts, and then through the centuries, various bits were added on and changed and upgraded, sometimes quite badly actually. It actually sits on the site of an original original college, St Mary's College, which was destroyed as part of the war between her and her sister. But that was actually, so there's a bit of incredible history there, and archaeology all tied into one. So it's of huge historical value. It's grade 2 listed, which if your listeners don't know is sort of the second tier, in simple terms, the second tier down, grade 1 being the kind of top tier of listed buildings in the UK. So they are officially protected. You can't just go in there and start hacking them up and insulating them. There is quite a significant approval process you have to go through with the local authority and their expert advisors. So it's student accommodation, but in need of significant refurb. It's not in great state, so the college are very proud of this building, but not the state that it's in, and wanting to upgrade it. And there's the opportunity: can we turn this into a low energy building? And so we've done that. We've got a design based around internal wall insulation, so wood fiber insulation lining the majority of the walls, not everywhere. There were some areas where we just couldn't touch it for historical reasons. Vacuum secondary glazing, so vacuum panels fitted behind the existing glazing. Again, we can't touch the existing glazing, so we're going to fit a second line behind them. Upgrades to the roof insulation. Ground source heat pumps, which were installed. That we installed the boreholes before they started any of the work on the fabric, so they were all installed, and so we've got a limited amount of heat available to us now from the ground. That's it. We've got to make this work now. So it's been quite an interesting challenge, and it's on site now. It's just been fantastic to start to see it go in. We've got photos actually of all the insulation piled up outside the building, and you've just got these stacks of insulation that we know are going to get fitted on these walls, mostly wood fiber. So mostly stuff which is biogenic and not made of petrochemicals, or not made of rock and limited resources, but renewable sort of insulation products and that sort of thing. So really exciting to see that actually happen.
Yeah, it sounds incredible. Was the wood fiber insulation choice mostly your firm's choice, or was that something the college was asking for?
It was between us and the architect. So the architect, Lee Fitzgerald Architects, they definitely had the kind of ethos of using natural materials and that sort of conscientious approach to buildings. I mean, the thing with internal wall insulation in particular is you've got to be very careful about moisture dynamics. So you need materials that respond in the right way to moisture, that buffer moisture and allow moisture levels to rise and fall to protect your building from the risk of condensation. So wood fiber insulation is the key kind of material for that, for most projects, and one that we could legitimately use and we were allowed to use. So they wouldn't let us use things that were, they being the local authority, they wouldn't let us use techniques or materials that couldn't later be removed. So that ability to, in theory, if for whatever reason they wanted to restore it to its original form, you could take all this stuff off. That was one of the principles we had to abide by. So that kind of drove some of those. And plus, the idea of putting in petrochemical insulation into this historic building was just didn't seem appropriate. So yeah, quite a few things, all driven really from technical and kind of best practice in terms of how you look after buildings.
Well, that sounds like a really great project. And I assume you'd have some kind of plaster on the internally?
Yeah, so lime plaster on the internal face of the wood fiber, which is breathable. So you've got something which is airtight and breathable on the inside, so it allows moisture to travel in both directions depending on the prevailing conditions. So the idea is just generally you're just trying to avoid trapping moisture between layers of the construction, where you get moisture build up in that construction. It's got somewhere it can get out. It can evaporate and move back through the structure and escape.
And is there a commercial kitchen facility in the building, or?
No, not this one. No. So this one has because the site has its own catering for students. So there's very limited sort of catering facilities in this. I think there's a kitchen of sorts, but nothing of that type. So no. So the building services, we've got MVHR supplying fresh air around the building. That's been an interesting one. The MEP consultant Edge Associates quite challenged there in how they threaded ductwork through this building. And similarly, to get approvals for that and where you can put ducts, where you can't, avoiding damaging historic fabric and so on.
Yeah, it sounds great. What's the timeline on that one?
It's on site now, so I can't remember the completion date, but I suppose within the next, I don't know, 6 to 8 months, we expected to get close to that one finishing.
Great. Well, that sounds I assume you'll be probably presenting on it at some point. It sounds like a great project.
Yeah, we definitely like to. We haven't made enough noise of it actually, because I think it's really exciting. And I was there with the architect on site and my colleague the other day, and we just looked at each and went, "This is amazing. We've got this far after all the kind of going through the hoops of getting the approvals and all the kind of technical challenges, and we can see the wood fiber insulation going in, and this building being transformed into a much lower carbon, low energy building, which hopefully will last the college another few hundred years. It's done them a good few hundred years first, so we've got to make sure we safeguard it for a few hundred more.
Yeah. Well, yeah, you have a timeline there that that you can see walking around, rather than here where, well, some of the buildings may be considered really old if they're 100 years old. So anyway, thanks so much for your time. I really appreciate it. And, look forward to hearing more about that project and others that you're working on.
Brilliant. Thank you very much, Mary.
And that was Chris Swinburn, who is the founding director at Beyond Carbon Associates in the UK. Great interview, Mary. What were the highlights for you?
Well, there were so many highlights. I mean, the conference that I went to focused on large projects, large complex projects. So, and that's exclusively what his firm does, which I thought was very exciting. And the growth of his firm in 3 years, so that he has now 16 people working there. But also, our conversation about that his firm will not work on a project that wants to include gas as a fuel. I thought that was great, and it fits in with our electrification theme this month. And the exciting news that in the UK, the grid is decarbonizing. So that was
Yeah. I couldn't help thinking about how those conversations might go if you didn't make that clear up front, that you sort of, obviously you would need to make that very, very clear to say, hey, we're not going to do gas. And if you are wanting gas, you need to find someone else to do your work.
Not something you bring up 2 months into a project.
Yeah. I mean, it does help to have those pretty strong policy indications that's the direction of travel for the country and also the industry. But it's really great to have organizations and individual companies making pretty strong statements like that. Yeah, the form factor one, that's really interesting, Mary. That struck me as well. He mentioned there are some complexities. It's not a given that a large building is going to be energy efficient, because there are lots of areas in a larger building for things to go wrong, particularly with air tightness and complex shapes. But in general, particularly when you're measuring things on a per square meter basis, as you are with Passive House, and just by the physics of the form factor, working on large buildings, it is simpler. Well, not necessarily simpler, but it can be easier to achieve some of those targets. But I thought it was really interesting talking about the different heating options and the fact that there's not one size fits all when it comes to both water heating and space heating. I often hear this conversation about, or the decision about, which is the best option for water heating on a large building, whether you go to a ring main with a large storage tank, or if you go to individual sort of more at source or instantaneous water heating. So obviously they settled on heat pump water heaters for this project. But I'm very interested in that space about, and the fact that there isn't necessarily a one single answer, but it requires a bit of analysis and cost benefit of the individual projects. And with regards to the space heating, I just wanted to highlight, I mean, he explained that quite well, but I just want to emphasize the decision there to go from, or not to use heat pumps, but to use electric resistance heaters, which are, as he said, 3 times more energy hungry than a heat pump. So, they're basically a 1-to-1 ratio of energy in, energy out, versus a heat pump where you get a lot more heat out than the electricity you put into it. But because the envelope is so much better, you don't actually need that much heating. And from a cost point of view, it's very, very simple to put in just an electric resistance heater in each room. And you also don't have, I mean, there's a lot of moving parts in a heat pump. So to have a system that is going to do that through the whole building, and also have individual control, once again, it's not necessarily a black and white, one size fits all solution. So I guess the underlying point there is the value of doing such a good job with your envelope means that you can make more value judgments or more cost benefit analyses on some of your systems. Zach, what were your thoughts?
Well, just piggybacking on what you just mentioned, he outlined how much larger the energy demand was for the domestic hot water compared to the space heating with a dormitory, and that problem, we have the Reimagine Buildings Electrification Conference coming up on January 24th, and it's really diving into what are the tricky parts of making a building all electric. And domestic hot water is one of the ones that's just really interesting, and there's lots of it depends answers and different approaches. So we'll really be focusing in on that, and also looking at really efficient delivery, the time between turning on the faucet and getting the water from the tap, that whole piece of the puzzle. So it was a really nice primer or teaser, I guess, for the sorts of topics that we're going to be diving into at the conference. The other thing that I just thought was so interesting was the historic nature of the retrofit that he's doing, and just that's so out of my like in the U.S. everything, even old buildings are brand new compared to what he's working on. So that was
From the 1600s?
pretty amazing. Yeah, exactly.
Especially when he talked about doing the future climate files and saying, he felt a bit stupid going out to 2080. It's like, well, that's nothing. You're working on a building that's 300 years old.
Yeah, exactly. And with a building like that, I sometimes am frustrated with the limits on high performance retrofits that can be placed on historic buildings. But if we're talking a building that's from 1600s and with that kind of history, all right. But yeah, really, really great conversation. Super interesting practice he's running.
Yeah. Yeah, I thought, obviously some huge challenges there. And I agree. I think, at some point, we had this debate a lot about the value of heritage and how you try and keep things the way they are. In those instances where even on the inside, you can't touch the envelope because someone has deemed it to be so important that you can't insulate it. Yeah, these are all, they're tough decisions and I don't think any single person can make those decisions either. That's the other tricky part of that, because if it was up to an engineer, they'd probably cover the whole thing. But that's why we have experts in heritage as well, and there are values that some of these things are worth preserving for different reasons.
Yeah, absolutely.
I was interested that the use of CO2 heat pump, Mary. I don't know if you've come across other situations where they've been in common use yet, because I thought they were still early technology.
Well, they've been around for a few years here. I actually have one at my house, and it's been, the kind of appliance that you want, right? You install it and it's no problems since.
Right.
So yeah.
For hot water, right?
I use it for hot water, but my heating system is water to air heating system, because it was a retrofit. and I already had all the ducts from my furnace in place. So kind of shoehorned it in to work, but it's been great. And yeah, I've heard it being used in a large building, the Sanco, before this, but I think only once. So yeah, it was exciting to hear about it being used in a larger building. But Zach, how about you? Have you heard it being used in larger buildings?
No, no. I mean, I think you're right that that's fairly new. I think that for a few years now, domestic hot water heat pump hot water heaters have been that are CO2 based have been applied to single family buildings. So I think we've at least in the US heard and seen a lot of examples of that. Sometimes, and there have been some problems, but it seems like things are getting worked out. But yeah, it's cool to hear about the application in a bigger building.
And just to for those that aren't up to speed with that, and while we're talking about this, is that it might be counterintuitive, but CO2, we talk about CO2 as we're trying to minimize CO2, but actually CO2 is the least damaging or least problematic of the other refrigerants that have been commonly used as the closed loop refrigerant in heat pump systems in the past, which have thousands of times greater global warming potential than CO2. So when Chris pointed out that the CO2, the global warming factor of CO2 is 1, it's because everything is measured against CO2. And what the alternatives are, I mean, they're in the thousands of times greater impact. It's sort of orders of magnitude worse. And we're talking, and this is because that's a closed loop on most heat pumps, but it's leakage and they will leak. It's a question of when they leak, not if they leak. So knowing that most systems will leak at some point, that's why the industry is trying to move towards CO2, because CO2 is much, much better than other refrigerants that are typically at lower pressures. I think that's one of the challenges with the CO2 is that it has to be at a higher pressure than some of the other refrigerants. But great to see those technologies being used and becoming more commonplace. So that's really good to see.
Yeah, no, that's a really good point. And if you go back to the decision to do electric resistance instead of heat pumps, given that you got a leakage rate in refrigerants of 5% a year or something like that. I mean, that's a number that Skylar Swinford has shared. That has a big impact on the climate impact of a building. So, that is just another way that the efficiency of the envelope helps to in many, if you need to think about the whole, use some systems thinking about the impact on the mechanical systems and therefore the volumes of refrigerants and therefore the impact of that leakage. So that could make that decision to go to electric resistance an even sounder one from a carbon perspective potentially, but
Yeah.
only because the heat demand is so low.
Right. And
Yeah.
so just wanted to highlight the controllers that goes with those electric resistance heaters, because that was impressive that they can detect whether there's someone in the room, whether there's a window opening. It detects the airflow into the room. So very smart controls controlling those electric resistance heaters.
Yeah, that's very cool about the detecting the window open, because you can have motion sensors or timers, but to say, hey, you've opened the window, so there's no point in having this heater on until you close it. There's some really good controls. At the same, that's a really good example, I think, of offering individual control, which is an important part of comfort. So you're still giving the occupant the ability to turn things on and off, but also recognizing that maybe college students aren't the most reliable at turning things off. So you've also got another layer of automation over and above that, which I think is quite a nice blend, because having no user control can also be problematic when you have a large and diverse population that you're trying to satisfy. You're going to have all different levels of comfort. Awesome. Really good stuff. Thank you for that, Mary. And as we said, really impressive growth rate for that company. I think that's a really good sign of the industry and the demand for passive house, but also their emphasis on carbon and just healthier design. And then well, hopefully it's more than just a small market. It's definitely a growing market in that space. So really, really good to see. All right, Zach, what have we got coming up on the accelerator?
Well, we are in full swing with Passive House Accelerator live episodes, Zoom gatherings every Wednesday. So join us for that. And we're exploring the theme of electrification this month. And the big event that we want to encourage everyone to take part in is Reimagine Buildings Electrification, our virtual conference, half-day conference on January 24th, that dives into the real challenges involved in electrifying buildings and the solutions that are being applied in the real world on all sorts of different building scales of building to address those challenges and create successful all-electric passive house and low carbon buildings. So it's going to be a great event. I hope people will join us. If you are a member of the Reimagine Buildings Collective, you can join us. The ticket is complimentary to all of our Reimagine Buildings conferences. Also, lots of cool stuff happening on the collective. We just started a new course that is a fireside chat-based course hosted by Michael Ingwe called Next Level: Secrets from the Pros. And the first 3 lessons will be 3 different fireside chats with Lois Arena of Stephen Winter Associates, Maureen Sanchez of RDH Building Science, and Ed May of Building Type. So 3 of the top passive house consultants in North America will be sharing their secrets and their tech stacks and how they make their practice hum. So lots of other stuff happening too, but that's probably that's probably enough for now.
Loads of stuff. I mean, when you bring up all these new events or activities or areas that people can gather on, and it seems like even one of those alone, like getting to have some one-on-one time or group time with Michael Ingwe, hugely valuable. So probably the worth the ticket price of admission just for that, as well as all the other great stuff that's in there. So definitely check that out if you haven't already. All right. Thank you very much, Mary. I really enjoyed that. And cheers, Zach. We'll be back again next week on Passive House Podcast.